Solve examples on series and alternating series. This video is only for online questions. So the example 1, the geometric series 1 upon 2, 1 upon 2 square, 1 upon 2 cube by nth root test. So here the un will be 1 upon 2 raised to n, and the nth root test is 1 by n. So this will be 1 upon 2 raised to n raised to 1 by n. So this is equal to 1 upon 2. So after taking limit n tends to infinity, un 1 upon n, the limit remains same, half, and this half is strictly less than 1, which implies the series 1 upon 2 raised to n is convergent. So the option C. The geometric, second question, the geometric series, this is again a geometric series, 1 plus 4 by 3 plus 4 by 3 whole square, again by nth root test. If we apply nth root test on this, the un is 4 by 3 raised to n. According to nth root test, I will take its nth root, so this will be 4 by 3 raised to n raised to 1 by n. So 4 by 3, and after taking limit n tends to infinity, un raised to 1 by n, this is again 4 by 3, which is strictly greater than 1. So by Cauchy root test, this series 4 by 3 raised to n is divergent. So the option number B. Example 3 is P series, where the value of P is 2, which is strictly greater than 1. So by P series test, this is convergent. Here P is 2. Example number 4. Example number 4 is 1 plus 1 upon root 2, 1 upon root 3, 1 upon root 4. This is again a P series, which can be written as 1 upon n raised to half. The root can be written as n raised to half, where value of P is half, which is strictly less than 1. So by P series test, this series is divergent. So it's divergent. Again, example number 5, this is also P series where power of n is 1, so value of P is 1, so this is again divergent. Which of the following series is convergent? Example number 6, all these are P series. The value of P is 0.9, which is less than 1, so this is divergent. N raised to half, this root is nothing but raised to half, and half is strictly less than 1, so this is again divergent. N raised to 2, P is 2, which is greater than 1, so this is convergent. P is 1, so this is divergent. Now the seventh example. The seventh example is the infinite series cos 1 upon n is cos 1 upon n is our un, its nth term. Its nth term is 1 upon n. So by necessary and sufficient condition for convergent of series, it must be limit n tends to infinity, un must be 0. So if this is 0, the series un may be convergent or may be divergent. So we will check the limit n tends to infinity of cos 1 upon n. So as n tends to infinity, 1 upon n tends to 0 and cos 0 is 1. So the limit of this un is not equal to 0, which implies the series cos 1 upon n definitely diverges. So this is divergent series. Example 8th. The infinite series 2 plus 1 upon n raised to n by nth root test. They are mentioning which test we have to use. So we are going to use nth root test for this series. So what we notice that here un is 2 plus 1 upon n raised to n, and if I use nth root test over here, so I will have un raised to n, which will be 2 plus 1 upon n raised to n raised to 1 by n. So this n cancels out, so 2 plus 1 upon n is the un raised to 1 upon n. Now let's take limit as n tends to infinity. So limit n tends to infinity, this is 2, and 2 is strictly greater than 1. So by root test, this series is divergent. Example 9th. So here un is 1 plus 1 upon n raised to n square. So again they have mentioned we have to use nth root test. So let's take its nth root. So this will be 1 plus 1 upon n raised to n square raised to 1 upon n. So un 1 upon n is 1 plus 1 upon n raised to n. Now let's take limit both the side as n tends to infinity. Limit n tends to infinity, and this is the standard formula. This is nothing but e, and the value of e is strictly greater than 1. So this series un is divergent. So this is divergent. So let's take example number 11th. Series 3 raised to n 4 raised to n by nth root test. What is un over here? It is 3 raised to n 4 raised to n. So by nth root test, un raised to 1 by n, this will be 3 upon 4. And after taking limit as n tends to infinity, limit is 3 by 4, which is strictly less than 1. So this is convergent series. Let's change the test for now let's take example number 14th example. is the infinite series. Here un is given by n plus 1 upon n square. Example 14th. What is un over here is n plus 1 upon n square, and how can I decide that this series is convergent or divergent? By using comparison test, because numerator consists of polynomial, this is also a polynomial. So by comparison test, I will take it out the highest power of n in the numerator. So this is n, and 1 plus 1 upon n square. So what I have is 1 upon n, 1 plus 1 upon n. So this is my Vn in comparison test. So Vn is 1 upon n, and the series Vn is series 1 upon n, which is a p series, and the value of p is 1. So this is divergent. Since this is divergent, and the limit un Vn as n tends to infinity is 1 upon n, 1 plus 1 upon n upon Vn. Vn is 1 upon n. So this is our un and this is our Vn. So this cancels out and the limit is 1, which is non-zero finite number. Which is non-zero finite number. So by comparison test, the series Vn is convergent, which implies this is divergent, so which implies series un is also divergent. So the series in example 14 is divergent series. Example 15th, again by comparison test, they have mentioned the un over here is 1 upon n square plus 1. So un is 1 upon n square plus 1. What it says, I have to take the highest power of n in numerator. There is no n, so this remains as it is 1, and highest power of n in denominator is n square. This is 1 and n square is outside of the bracket, so 1 plus 1 upon n square. So the common portion is 1 upon n square. So this will be my Vn. So 1 upon n square. And observe that if I make series of this Vn, this series is again p series where p is 2, which is greater than 1. So which implies this is convergent. Since this is convergent, this is also convergent. So this is convergent series. Now take example number 17th. Example number 17th. By comparison test, the series is what they want. The series must be convergent for what conditions on P and Q. So let's find it out by comparison test. So what is un? Un is n plus 1 raised to p upon n raised to q. The comparison test wants the highest power of n in numerator outside. So this will be n raised to p and 1 plus 1 upon n raised to p upon, and the highest power of n in denominator is itself n raised to q, so n raised to q. So this will be my common portion in numerator and denominator, and I will take it as my Vn. So Vn will be 1 upon n raised to q minus p. So this n raised to p will come in denominator with n raised to minus p. So this is my Vn, and if I try to make series of Vn, so this will look like 1 upon n raised to q minus p. Observe that this is again a p series where the value of p is q minus p, and we need this series to be convergent. This series to be convergent means the series Vn have to be convergent. Since this is convergent, the value of q minus p must be strictly greater than 1, so which implies q minus p must be strictly greater than 1. Therefore, q greater than 1 plus p. So the option number first is the option number A is the correct one. Now again, let's change the test. Let's take example 19. They are asking for ratio test. So the given series is this. What is my un? Un over here is example number 19. Let's take example number 19. Un is n square upon n factorial. And the ratio test wants un plus 1. This will be un plus 1 whole square upon n plus 1 factorial. So next I will take the ratio of un plus 1 upon un. So this is my un plus 1. So I will write this in numerator, n plus 1 whole square upon n plus 1 factorial upon un. So I am going to write in denominator, or I am going to multiply this by inverting it. So n factorial upon n square. Observe that this n plus 1 factorial contains n factorial. So this will be cancelled from this, and I will have n plus 1 over here. So un plus 1 upon un is n plus 1 whole square upon n plus 1. N factorial and n factorial cancels over here, so this is 1 upon n square. So there is n plus 1 square and 1 n plus 1, so this also cancels out. So finally I have un plus 1 upon un as n plus 1 upon n square. Now this will look like 1 upon n plus 1 upon n square. Now I will take limit on both the sides of taking limit n tends to infinity of un plus 1 upon un is equal to, as n tends to infinity, 1 upon n is 0, so this is 0, and 1 upon n square is also 0, so 0 plus 0 is 0, and 0 is strictly less than 1. So by ratio test, the series n square upon n factorial is convergent. Is convergent. Now let's take example number 20. Example number 20 is again by ratio test. What is my un over here is un is 3n minus 1 upon 2 raised to n. What I will do, I will take un plus 1, I will find un plus 1th term. This will be 3n plus 1 minus 1 upon 2 raised to n plus 1. So I can write it as 3n and into 3, so this is 3n minus 1, so 3 plus 2 upon 2 raised to n. Laws of indices will allow me to write this as 2 raised to n into 2. And the ratio test wants this ratio un plus 1 upon un, so this is equal to, I will write this as it is, 3n plus 2 upon 2 raised to n into 2 upon this thing, or into 2 raised to n, and this will be in inverse manner, so 2 raised to n 3n minus 1. So this 2 raised to n cancels out, and what I have is this half, this 2 as half, 3n plus 2 upon, this is 3n minus 1. So this is my un plus 1 upon un. Now I am going to take limit over this. Now take limit as n tends to infinity. So limit n tends to infinity, un plus 1 upon un will be half times, I will take it out n common from this. So limit n tends to infinity, n outside, so 3 plus 2 by n, 3 minus 1 by n cancels out. As limit n tends to infinity, this is 0, this is 0, I have 3 upon 3, which is 1. So answer is half into 1. So this is half, and half is strictly less than 1. So again, by ratio test, this series is convergent. So this is convergent. Let's take this example number 22. What it says that they have given the series and they are asking only what is the limit of un upon un plus 1. So they are not asking about is it convergent or divergent. So I just need to find the limit of this term un upon un plus 1. So observe that what is my un is example number 22. So I will write down the un nth term. So given that un is 2 into 5 into 8 into 11 into 3n minus 1 upon 1 into 5 into 9 into 13 into 4n minus 3. So this is my un, and what they want is un plus 1th term also. So un plus 1th term will be 2 into 5 into 8 into 11 into 3n minus 1, 3n plus 1 minus 1 upon 1 into 5 into 9 into 13 into 4n minus 3, 4n plus 1 minus 3. And they want the division of these two terms. If I divide un upon un plus 1, so I am going to divide this thing. So what I observe that 2 cancels out, 5 cancels out, 8, 11, everything cancels out, 3 raised to 2, and so it cancels out. So this cancels out up to here, everything. So what I have is 1 upon this portion. So un upon un plus 1 is nothing but this will go in numerator like this, 4n plus 1 minus 3 upon 3n plus 1 minus 1. Try to solve this. This will be 4n plus 4 minus 3, so this is plus 1. 3n plus 3 minus 1, so 3n plus 2. Let's take it out, n common from here, so this will be 4 plus 1 upon n, and n common, 3 plus 2 upon n, then n cancels out. Then it's time to take limit. So n tends to infinity, I'll take limit n tends to infinity. So this is 0, this is 0, so I'm left with only 4 by 3. So answer is 4 by 3. So answer is 4 by 3, A option. Now let's take example number 24th. Example number 24 says the power series 3x raised to n. What is my un? Un is 3x raised to n. And again they are saying that use ratio test and they want convergent. So for what value of x this is convergent? So ratio test, I want un plus 1 in ratio test. So what will be my un plus 1? This will be 3x raised to n plus 1, and I'll take un plus 1 upon un. So this will be 3x raised to n plus 1 upon 3x raised to n. So I have 3x raised to n into 3x upon 3x raised to n. Cancels out. So what I'm left with is un plus 1 upon n 3x. So this is 3x. So now let's take limit. N tends to infinity. N tends to infinity. So there is no n. So limit remains as it is, 3x. Now I want this series to be convergent, because they are asking by using ratio test the series is convergent for what value of x. So I want this to be convergent. So this is convergent only if this limit is strictly less than 1. So which implies x is strictly less than 1 upon 3. So let's see which example, which option. So x is strictly less than 1 by 3, 24th option A. Let's solve example number 27th, the nth term of this alternating series. So this is alternating series. So they are asking just nth term. So this will be 1 upon root n, and for alternating there has to be minus 1 raised to this. This is not alternating, this is not alternating, because the power is 2 raised to n. So the option D is correct one. Again, the example 28, the nth term of an alternating series. Let's look at this. This is very simple to solve. Log n upon n plus 1. So log n upon n plus 1. And for alternating sign, there has to be minus 1 raised to n plus 1. So option D is correct. Now let's see example number 29th. By Leibniz test, given alternating series 1 minus 1 upon 2 square, the nth term is this. So Leibniz test 20, which question? 29th. So the given series is minus 1 raised to n plus 1 upon n square. So what I have written, okay, minus n minus 1. So never mind. So this is n minus 1. So here un is only 1 upon n square. So observe that limit un as n tends to infinity is 0. This is my first condition for Leibniz test. And the second one is un is 1 upon n square, and un plus 1 is 1 upon n plus 1 square. Obviously this is greater than un plus 1, which implies un is a decreasing sequence. So by Leibniz test, this is definitely convergent. Similarly, they both are same question. Let's change. Again, by example number 32, by Leibniz test, this is again convergent, because this is decreasing and limit n tends to infinity of un is 0. Let's take example number 35. So it says that series 2 raised to n plus 1, 3 raised to n plus 1. So my un is 2 raised to n plus 1, 3 raised to n plus 1. So let's take it out. 2 raised to n common from here. Two raised to n, 1 plus 1 upon 2 raised to n, and 3 raised to n, 1 plus 1 upon 3 raised to n. So the common portion is this. So my Vn is 2 raised to n upon 3 raised to n. This is nothing but 2 raised to 3 raised to n. And if I take the series of this Vn, so this will be series 2 raised to 3 raised to n. And this is the geometric progression. So this geometric progression is convergent if this 2 by 3 is strictly less than 1 and this is strictly less than 1. 2 by 3, the value of 2 by 3 is less than 1. So this is convergent series. This is convergent. So by comparison test, this is convergent. Sorry. So this is convergent series. Example number 36. The series is the un over here is root n upon n square plus 1. So what I will do, I'm going to use comparison test over here. So I'm going to take the highest power of n in numerator. So n raised to half, 1 upon n square outside, 1 plus 1 upon n square. So what it will become, 1 upon n raised to 2 minus half and 1 plus 1 upon n square as it is. So un, so this is my common portion, which is my Vn. So this is my Vn is 1 upon n raised to 2 minus half is 3 by 2. So again I am going to make it as a series, and the value, this is P series and the value of P is 3 by 2, which is strictly greater than 1. So this is convergent. So this is convergent, which implies the original series is convergent, which implies the given series in example 36 is convergent. So this is convergent. 37, this is geometric progression. This is 1 by 2, 1 by 2 square, 1 by 2 cube, and the common ratio is half, which is convergent. This is oscillatory.